So now let's talk about the dot product. So the dot product is sort of like a meaningful way of multiplying two vectors together. So another word for the dot product is the scalar product. So the scalar product, the dot product is also called the scalar product because when you do the dot product, you just result in a number. It just gives you a scalar. So be careful, don't confuse scalar product with multiplying a vector by a scalar. They're different things. The scalar product is a dot product, whereas multiplying by a scalar is just multiplying a vector with a scalar, as its name suggests, whereas the scalar product is the dot product. So, yep, the notation for the dot product is we use this little dot, hence why it's called the dot product, and it will always result in a scalar quantity, and the dot product can be calculated in two different ways. So geometrically, the dot product of two vectors is the product of their magnitudes and the cosine of the angle between them. So if we take the dot product of A and B, we can just find it. But if we have the magnitude of A and we multiply that with the magnitude of B, and then we multiply that with the cosine of the angle between those two vectors, that will give you the dot product. Algebraically, though, if you have the two vectors in component form, you can get the dot product by sort of just summing the products of each of the two vectors corresponding components. So if you have x1i and y1j, and then you have x2i and y2j, the dot product will just be x1, x2 plus y1, y2. And you will get a scalar. You will just get a simple number when you do the dot product. And these expressions are equivalent, so they will give you the exact same thing. So both these formulas will give you the dot product. So there are some particular cases of the dot product which you need to know. Since the dot product is going to be the product of the vectors' magnitudes as well as the cosine of the angle between them, we have some special cases depending on what the angle is between them, because we know with the cosine graph, it looks like this. So this is 90 degrees, 180 degrees, 270, and 360 degrees. So basically, when theta is equal to 90 degrees, cos theta will be 0. So if this is 0, the dot product will be equal to 0. If cos 90 degrees is 0, that means if A and B are perpendicular, that means that the angle between those two vectors will be 90 degrees. And therefore, the dot product will be 0. So if they're perpendicular, the dot product between A and B will be 0. And if they are going the same direction, if theta equals 0, we know cos 0 is 1. So if they're going in the same direction, cos 0 becomes 1. So it will simply just be the magnitude of the vectors together. Which means if we have the same vector dot product with itself, because the magnitude is going to be the same, so if we take the dot product of A with A, it's just going to be the magnitude of A times the magnitude of A, which is just going to be magnitude of A squared. So these two results are super important. You use them a lot in geometric proofs and any questions here in vectors. So make sure you know these results. The dot product of a vector with itself is just the magnitude of that vector squared. And the dot product of a vector, the dot product of two vectors will be 0 if those two vectors are perpendicular. And using this geometric formula for the dot product, we can actually rearrange it so that we can say cos theta is equal to the dot product of A and B divided by the magnitude of A multiplied with the magnitude of B. So that if you're asked to find what the angle is between two vectors, you can actually just use this to help you find the angle between the two vectors just by rearranging that dot product formula. So with the dot product, it follows some rules which you need to make sure you're aware of. So we have the commutative law, so that the dot product of A and B is the same thing as the dot product of B with A. So the order doesn't matter. It's sort of like normal multiplication. 2 times 4 is equal to 8, which is equal to 4 times 2. Doesn't matter which order you do it. We also have the associative law, which basically means if we have a scalar, where k is a scalar, it can be multiplied with a first, then before you do the dot product of b, or you can just multiply it directly to the dot product of a and b, or you can just multiply it first to b before taking the dot product of that with a. It doesn't matter. You can just move around the scalar, it will still work. And then we have the distributive law, which basically says you can sort of expand brackets like how you would expand normal multiplication. So if we have the dot product of a with b plus c in brackets, that's the same thing as the dot product of a with b added with the dot product of a with c. So you can sort of expand the brackets like that. So let's just do some questions together to sort of put that into practice. So our first question is, we want to use vectors to prove the cosine rule. So we want to show that for a triangle with sides a, b, and c, that c squared equals a squared plus b squared minus 2ab cos c. So this is a different proof to another question you might be asked, which is to use the cosine rule to prove the equivalence of dot product of a, to prove the equivalence of magnitude of a multiplied with magnitude of b multiplied with cosine theta is equal to x1, x2 plus y1, y2. That's a different proof to the one we're currently doing here. But I recommend in your spare time trying to do this proof here. It's really fun. You can use the cosine rule to do that. But here we're going to do a different question. We're going to use vectors to prove the cosine rule instead. So let's just let this vector here be a, and let's just let this vector here be b. So therefore c, we can say that this vector here is going to be a minus b, like so. So now we want to use vectors to prove the cosine rule. So we're trying to show that c squared is equal to a squared plus b squared minus 2ab cos c. So c squared, the length of c here, is the length here is the magnitude of a minus b. And c squared, therefore, will be the magnitude of a minus b squared, the length of this vector squared. And the thing is, we know that with the dot product, we said that when we take the dot product of a vector with itself, we get the magnitude of that vector squared. So therefore, the magnitude of a minus b squared is simply just going to be the dot product of a minus b with itself, like so. And now we can use the distributive law to sort of expand the brackets here. So we can sort of expand the brackets like we do normally with multiplication. So this will be dot product of a with a, minus dot product of a with b, minus dot product of b with a, plus dot product of b with b. And this will give me magnitude of a squared. And here's the thing, dot product of a with b is the same thing as dot product of b with a, using the commutative law. So therefore we can collect those like terms together. This dot product of b with b will simply just be magnitude of b squared. And here we'll get minus 2 times dot product of a with b. Now here's the thing, we also know the geometric definition of the dot product is going to be, we can say that dot product of a with b will simply just be a, magnitude of a times magnitude of b, times cos whatever the angle is between them. In this case, the angle between vectors a and b is just going to be capital C. So remember, magnitude of a minus b squared, we said that's equal to c squared. So magnitude of a squared, vector a squared, is just going to be a. And the magnitude of b, the vector b, is just b, so b squared minus 2ab cos c. And therefore, we've proven the cosine rule, like so, just using our knowledge of the dot product. So yeah, again, this is a different question compared to if you were showing the equivalence. That is also another fun question. I recommend doing that in your own time. Okay, so here's another question. We have a semicircle APB, whose diameter is AB. So we let OA be the vector A, and then OP is the vector P, like that. So we're asked to prove that angle APB is going to be 90 degrees. So we can say that vector AP is going to be, using our knowledge of vector subtraction, so OA is, so OA is the vector A. So AP, it's a vector drawn from A pointing to P, so that's going to be P minus A, like so. That's AP. So if we could show that vector AP is, if we can show that it's perpendicular to vector BP, then we can show that this angle here will be a right angle. So we want to show that the dot product of those two vectors is equal to 0. So, but now we need to express BP in terms of P and A. So the thing is, this vector here is P, OP is P, and this vector OB is going to be the negative A because it's the same length because it's the radius of a circle, but it's going the opposite direction as OA. So therefore, BP is going to be, using vector subtraction, it's pointing to P, so it's going to be, so BP is equal to P minus OB, which is going to be minus A. So in actuality, BP is actually going to be P, vector P plus A. Another way you can visualize this is you can actually say that when we add vector P, when we take BO, this is also the same thing as vector A. This vector plus this vector here will be BP. So that also works too. So we know that BP is going to be P plus A. So now we know we have expressions for AP and also BP in terms of P and A. So what I can do now is I'm going to take the dot product of them. So the dot product of AP with BP is going to be the dot product of P minus A with the dot product with the vector P plus A. So now I can expand it using the distributive law of the dot product. So this will be dot product of P with P plus dot product of P with A minus dot product of A with P minus dot product of A with A. So this will be magnitude of P squared. Using the commutative law, these things are equal, so when we subtract them from each other, they'll cancel. And then the dot product of A with itself, which is going to be the magnitude of A squared. So we have these two results now. But the thing is, we notice this is a semicircle. So if we go back to our initial vectors, OA is this vector here, and OP is this vector here. But this is a semicircle, and OP is also a radius of the circle. And in a circle, the definition of a circle is all the points equidistant from the center. So all the radii, the radius should be the same as each other. So all the radii are equal. So we can say, but magnitude of P is equal to magnitude of A because radii of the same circle are equal. So therefore, if that's equal to each other, therefore this thing is equal to 0. Because if the lengths are equal, when we square them together and subtract them from each other, they're still going to be 0. So therefore, we can say that AP is perpendicular to vector BP, and therefore angle APB is 90 degrees, like so. So for part B, they're asked what circle geometry theorem have we proven? Basically, P is just any point here. It's basically saying in this, it's basically saying that in the semicircle, so here, this is 90 degrees, APB. but P could have been any point on this semicircle. It could have been here or here. Basically, no matter what you do, you're going to get right angles. So if you recall, if you ever did circle geometry in junior school, like in year 7 to 10, you'll know that in a semicircle, the angle subtended at the circumference by the diameter will be a right angle. So that's basically the circle geometry theorem we've just proven, which is really cool, using vectors to do that.